As we know that finite element analysis is not only used for structural problems, it can also be used for complex structures. A complex structure may or may not be having straight edges. So isoparametric elements are used for the curved edges. Now let us see in detail about isoparametric elements in finite element analysis. So in order to take care of the curved boundaries, refined meshes are to be used, and when the straight edged elements are employed. The isoparametric concepts are brought out by Tait and later generalized by B.M. Hines. He revolutionized the finite element analysis, and it also helped in properly mapping the curved boundaries. Both Hines and Tait brought out the concept of mapping regular triangular and rectangular elements in natural coordinate systems to arbitrary shapes in global systems as shown as in the figure. So this is the parent element in the natural coordinate system, and after mapping to a global coordinate system, the rectangular 3-noded or 5-noded rectangular elements will have the curved systems. The parent element in the natural coordinate system is mapped to global systems. Similarly, the rectangular 4-noded rectangular element is mapped to global systems by using isoparametric concepts, and the rectangular elements with more than 4 nodes. So in this case, the rectangular element has 8 nodes that is mapped by using quadratic curves. So as the number of nodes increases in the rectangular element, the cubic curves can also be used for mapping into global systems. Similarly, for three-dimensional elements, it can be mapped by using isoparametric element in this way. So as the node increases, the curved edge tend to choose cubic curves. So in isoparametric element, the natural or local coordinate system must be mapped to global coordinate system. So in finite element analysis, we have used the shape function for defining the deflection at any point in terms of the nodal displacement. Tait suggested to use the shape function for the coordinate transformation from natural local coordinate system to global Cartesian system, and successfully achieved in mapping parent element to required shape in global system. Thus, the Cartesian coordinate of any point in element may be expressed as, with the help of a shape function, for x is equal to n1 x1 plus n2 x2 up to nn xn, and y is equal to n1 y1 plus n2 y2 plus up to nn yn. In z direction, the shape function n1 z1 plus n2 z2 up to nn into zn. So in short, in the matrix form, we can write the coordinate transformation as x is equal to n into xe, where n is the shape function, x or xe are the coordinates of nodal points of the elements. The shape function are to be expressed in natural coordinate systems in isoparametric elements. For example, consider mapping a rectangular parent element into a quadrilateral element as shown in the figure. So the parent element has a straight edges with 4 nodes, whereas the mapped element has an unequal length with 4 nodes as shown in the figure. So while mapping, the local coordinate system is converted to global Cartesian coordinate systems for this rectangular element. So based on the previous example, the 4-noded rectangular element is mapped to a quadrilateral element by using global Cartesian coordinate system. So here we can see in the parent element, the 4-noded rectangular element has node 1, 2, 3 and 4, and their coordinates are -1, -1, -1, 1, 1, 1, 1, -1. By using the shape function, the global coordinate system can be obtained by using this equations. N is equal to 1 minus epsilon into 1 minus eta by 4. N2 is equal to 1 plus epsilon into 1 minus eta by 4. Similarly for N3 and N4. So in global system, the coordinates of the nodal points are represented as x1 to x4 and y1 to y4 in all the 4 nodes. To get this mapping, we define the coordinate of the point P. So in x direction, with the help of shape function and global coordinate system x1 to x4, we can write the equation as x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Similarly for y is equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. So it should also be noted that the shape function at node I, ni is equal to 1, and all the others are 0, thus satisfy the coordinate value at all the nodes. Thus at any point in a quadrilateral is defined in terms of nodal coordinates. Similarly, the other parent elements are mapped suitably when we do coordinate transformation. In mapping of isoparametric element, the isoparametric concept is developed based on following 3 basic theorems. The theorem 1, if the 2 adjacent elements are generated using shape function, then there is a continuity at the common edge. If the parent element is mapped to isoparametric element, the continuity exists at the common edge. The common edge here is the node that is connecting these two elements. And the same continuity will be followed in isoparametric element as well. And theorem 2, it states that if the shape function are used such that the continuity of the displacement is represented in the parent coordinates, then the continuity requirement will be satisfied in the isoparametric elements also. So the continuity that is developed and maintained in the parent element will also be maintained in the isoparametric element. So theorem 3 states that the constant derivative conditions and the conditions for a rigid body are satisfied for all isoparametric elements. If the algebraic sum of ni is equal to 1, we can see the proof by taking the displacement function u is equal to alpha 1 to alpha 4, and the nodal displacement at ith node is given as ui is equal to alpha 1 to alpha 1 plus alpha 2 into xi up to alpha 4 to zi. So in finite element analysis, we define nodal displacement at any point in the element in terms of nodal displacement as u is equal to algebraic sum of ni into ui, and by using this displacement function and from the isoparametric concepts, we know that summation of ni into xi is equal to L, summation of ni into xi is equal to x, similarly for summation of ni into yi is equal to y, and for summation of ni into zi is equal to z. So by using these conditions and isoparametric concepts, the theorem can be proved. Hence, they can safely used for this isoparametric representation. The shape function developed in the natural coordinate system satisfies the current requirements, and this theorem is known as convergence criteria for isoparametric elements. So in isoparametric element, the uniqueness of mapping are described here. It is absolutely necessary that a point in a parent element represents only one point in the isoparametric element after mapping. Sometimes, due to the violent distortion, it is possible to obtain undesirable situation of non-uniqueness. So, if this requirement is violated, determinant of Jacobian point that is represented in the parent element after mapping should also be represented by one point in the isoparametric element. So, from this picture, we can see the uniqueness of mapping in isoparametric element. So, the point that is represented in the parent element after mapping into an isoparametric element should also be represented by the same point, so that the accuracy of the solution will be maintained in finite element analysis of isoparametric elements. Let us see the different classifications of isoparametric element. Let us see the classifications of these elements that is termed as an isoparametric element which will have curved edges. So the basic element is isoparametric and it is categorized into the other. So when the isoparametric elements are used to the shape functions for defining the geometry as well as displacement. If these shape functions are used for defining the boundary and displacements, so we have seen that in the finite element analysis with isoparametric elements, the shape functions are used for defining geometry as well as displacement. If the shape functions defining the boundary and the displacements are same, the element is called as isoparametric element. In an element in which more number of nodes are used to define geometry compared to the number of nodes used to define displacement, it is known as superparametric element. In the stress analysis, where the boundary is highly curved but the stress gradient is not high, one can use these elements that can be useful and it is advantageous. Subparametric elements are the one in which less number of nodes are used to define geometry compared to the number of nodes used for defining the displacements. Such elements can be used in case of geometry being simple but stress gradient is high. Let us see the isoparametric, superparametric and subparametric element in the form of figures. Here the circle represents the node that are used for defining the geometry, and the square symbol is used as a node used for defining displacement. So as you can see, the isoparametric element in which nodes is used for defining both geometry and displacement, whereas in superparametric, number of nodes used for defining geometry and defining the displacements are equal, whereas in subparametric, number of nodes defining the geometry will be less when compared to the number of nodes defining the displacements. In isoparametric element, assembling stiffness matrix is a major part in finite element analysis. Since it involves a coordinate transformation from natural local coordinate system to Cartesian global system, isoparametric element needs special treatment. So the procedure can be easily extended to higher order element by using suitable functions and noting the increased number of nodes. Now let us take a 4-noded rectangular element that is to be mapped to an isoparametric quadrilateral element, and we also see how the assemblage of stiffness matrix is done in this example. So let us take a 4-noded rectangular element as a parent element, and we are mapping into isoparametric element using quadrilateral element. In case of a parent element, the shape functions are for ni is described on the slide. Since it has 4 nodes, we will have 4 shape functions. We use this above functions for defining the displacement as well as for defining the geometry of any point within the element in terms of nodal values. When we use the shape function, which can be written like this: x, y is equal to n1 to n4 in the first row, similarly in the second row, along with the displacements from x1, y1, x2, y2 up to x4, y4 for all the 4 nodes in the isoparametric element. Similarly, to describe the displacement using the shape function, it is represented in terms of u1 v1, u2 v2 up to u4 v4 on all 4 nodes. In order to assemble the stiffness matrix, we need the derivatives of the displacement with respect to the global xy system. It is easy to find the derivative with respect to local coordinates psi and eta, but it needs suitable assembly to get the derivatives with respect to global Cartesian system. So to assemble the stiffness matrix, we use a Jacobian matrix. The matrix J shown in the slide is known as Jacobian matrix. It relates the derivative of the function in local coordinate system to the derivative in global coordinate system. In case of a 3-dimensional problem, the Jacobian matrix will be in case of a 3-dimensional problem, the Jacobian matrix is given as shown in the slide. Now let us go back to the isoparametric quadrilateral element, and in order to get the Jacobian matrix, let us take for the Jacobian matrix at node 1 and 2 with respect to the natural coordinate system epsilon and eta, and with the help of shape function, the Jacobian matrix can be derived, and by substituting the value of I from 1 to 4 for any specified point, the above matrix can be assembled for Jacobian matrix like this. For the mapping of an parent element to an isoparametric element, the inverse of the Jacobian must also be used, which is known as Jacobian inverse matrix. So by knowing the Jacobian inverse matrix with this transformation relation, we can express the derivatives of the displacements as shown below, where J represents Jacobian matrix with the displacement u, v along with the natural coordinates eta and epsilon. So based on the strain displacement relationship for a 2-dimensional element can be taken, and that can be used for finding the strain in isoparametric elements. So the element stiffness matrix for an isoparametric element is given as K is equal to double integral of B transpose D into B into dx into dy, where T is the thickness, and it can also be shown that the elemental area in the Cartesian coordinate x, y can be expressed in terms of an area in the local coordinates epsilon and eta. So the element stiffness matrix for an isoparametric element is given as K is equal to T into double integration of B transpose D into B, where T is the thickness of the element and B is the strain displacement matrix and D is the displacement matrix. By using this relationship, we can get the stiffness matrix. But for the transformation of local to global coordinate system, Jacobian matrix must be involved. So the element stiffness matrix for the global element stiffness matrix for an isoparametric element is given as T into double integral of B transpose D into B into J with the natural coordinate system epsilon and eta. So this global stiffness matrix for an isoparametric element is given as K is equal to D E into double integral of B transpose D into B into J, where J is the determinant of Jacobian matrix. Since finite element analysis using isoparametric element involves too many mathematical calculations, and that is not suitable for hand calculation. So most of these isoparametric elements can be solved by using software tools. So using computer programs or using software packages, these isoparametric elements can be used. So in order to understand how the isoparametric elements are numerically solved, let us take one example for an isoparametric element by finite element method. So assemble a Jacobian matrix and a strain displacement matrix corresponding to the Gaussian point of 0.57735 and 0.57735 for the element shown in the figure. Then indicate how to proceed to assemble the element stiffness matrix. As I've already told you, Solving isoparametric element by using finite element method involves a lot of numerical calculation, but here it has asked us to show us in this numerical example it was asked to assemble element stiffness matrix with these two Gaussian points. So this is the given question, and the coordinates, the Gauss points are given as 0.57735 and 0.57735. So based on the given condition with the Gauss points, the coordinates of the node points in the Cartesian systems are 0, 0, 60, 0, 65.735, 10 and 5.735, 10. The corresponding shape function is given as ni with the local coordinates eta and epsilon. By using the value of the coordinates, the shape function n1, n2, n3, n4 can be obtained with the natural coordinates eta and the shape function for the natural coordinate epsilon. When the shape function is known, the Jacobian matrix can be determined. The determinant of the Jacobian matrix can be determined by using this equation. And the Jacobian matrix for the corresponding shape function from n for ni with x and y direction. So when the Jacobian matrix is the inverse of the Jacobian matrix needed to be find out. When the determinant of the Jacobian matrix is determined, the inverse of the Jacobian matrix must also be determined. Then using the strain displacement matrix, the strain displacement matrix is given as J11, J12, 0, 0, 0, 0, J21, J22, J21, J22, J11 and J12. By substituting the value of the shape function, the strain displacement matrix can be found out along with the inverse Jacobian inverse matrix. Since this example is to show how stiffness matrix for this isoparametric element, the displacement matrix can be assembled for the plane stress or a plane strain as the case may be, but by using material properties of the structure, in the following matrix multiplication may be carried out to assemble the displacement matrix. So by using this relationship T by 2 B transpose D into B, where B is the strain displacement matrix and D is the displacement matrix, with the use of Gaussian points we can find the element stiffness matrix. So with the use of the Gauss points we can find the element stiffness matrix of the size 3 by 8.